There are a million ways to tell a computer what to do, to give it instructions. But what if I told you some ways are just fundamentally different, like on a philosophical level? Today, we're going to unpack one of those really different ways of thinking by looking at a programming language called Haskell. It has a pretty unique approach to solving problems. Okay, so let's start with something super simple, adding up all the numbers from 1 to 10. Now, if you've ever written a line of code, this probably looks pretty familiar. This is Java, and it's basically a series of steps, right? First, you create a variable called total and you set it to 0. Then you loop from 1 to 10, and with each number you add it to that total. It's a very clear, step-by-step recipe. And now, get ready. Here's how you do the exact same thing in Haskell. Yep, that's it. That's the whole thing. Sum 1 to 10. Now, obviously it's super short, but what's really important here is that it's not a list of steps. It's a description. It's just saying, the answer I want is the sum of the list of numbers from 1 to 10. And that right there is the big question, isn't it? We've got two pieces of code. They get the exact same result, but they look and feel like they come from totally different universes. So how is that possible? Well, that's what we're going to dig into. The massive difference between that Java code and the Haskell code, well, it all comes down to a whole different philosophy of programming. And that philosophy is built around one single powerful idea: functions. So here it is, the key definition. In functional programming, you're not really giving the computer a sequence of commands to change things around. Instead, the main way you get anything done is by applying a function to some data, which then produces a totally new result. And this focus on creating new things instead of changing old ones, well, it has this huge side effect. It makes your code way more predictable and a lot less likely to have certain kinds of bugs. Let's put these two philosophies right next to each other so you can see what I mean. On one side, you've got the imperative style, like our Java example. Its main tool is variable assignment, changing the value of things like we did with that total variable. It's all about describing how to get the answer. But on the other side, you've got the functional style, like Haskell. Its main tool is function application. It doesn't care about the how. It just describes what the answer is. Here's a really good way to think about it. Imperative programming is like a recipe for a cake. First, you preheat the oven, then you mix the flour and sugar. It's a sequence of commands. Functional programming, though, is more like a mathematical machine. You just put your ingredients, your inputs, in one end, and a cake, the output, comes out the other. You don't have to know or even care about all the little cogs and gears turning on the inside. Now, this really elegant idea of just describing what you want instead of how to get it, well, it didn't just pop up out of nowhere. It actually has this fascinating history that goes back almost 100 years, long before most of the computers we use today even existed. The seeds for all this were planted way, way back in the 1930s by a mathematician named Alonzo Church. He came up with something called the lambda calculus, which sounds complicated, but it's basically a really simple, powerful set of rules for thinking about how functions work. It wasn't even a programming language. It was a pure mathematical system for talking about computation. Okay, now let's jump forward a couple of decades to the 1950s. A computer scientist named John McCarthy took inspiration from that lambda calculus and created Lisp, which was the very first functional programming language. But here's the thing. Early computers were all built around step-by-step instructions, so Lisp was kind of a hybrid. It had all these amazing new functional ideas, but it still held on to some of the old ways, like changing variables. The quest for a purely functional language was really just getting started. And you can see that long road right here. It starts with Alonzo Church's pure theory back in the 30s. Then Lisp takes the first practical steps in the 50s. After that, ML comes along in the 70s and adds some more modern features. After like 50 years of all this research and dozens of different languages, a committee finally got together in 1987, and they had one really ambitious goal: to create a new standard for pure functional languages. And that brings us to the grand finale of this 50-year journey. The goal wasn't just to make another language. It was to take all the best ideas that had been bubbling up for decades and put them all together in one place. And the result of all that work from that international committee was Haskell. It was designed from day one to be the new standard bearer for this whole different way of programming. It was advanced, pulling in all the best ideas from academic research, and, most importantly, it was purely functional. It completely embraced that mathematical machine idea with no compromises. And hey, this wasn't just some weird experimental project. By 2003, the official Haskell report was published, which defined a stable, mature version of the language. This report basically cemented Haskell's place in the world, taking it from a cool academic idea to a stable, powerful tool that was ready for serious use. So, as you can see, the whole journey to Haskell wasn't just about finding a shorter way to write code. It was about developing a completely different philosophy for how to even think about solving problems with a computer. And if you want to see what this philosophy can really do, just look at this. This is the code for quicksort. It's one of the most famous and efficient ways to sort a totally scrambled list of things. You don't even have to be a programmer to see how clean this is. The code basically just reads like a definition of a sorted list. It says, to sort a list, take the first item, then put all the stuff smaller than it on the left, then put our item in the middle, and then put all the stuff bigger than it on the right. It's just a description. So here's the thing to remember. This whole philosophy of function application isn't just some nerdy academic detail. It directly leads to code that's often safer, way easier to test, and because it avoids all these complicated moving parts, it's often much easier to run on today's multi-core processors. It's a really practical approach with some serious real-world benefits. And that kind of leaves us with a final, pretty big thought to chew on. What if the best way to solve our most complex problems isn't about writing a super long list of instructions, but instead about simply and elegantly describing the relationships between all the pieces? What new kinds of solutions could that way of thinking unlock?